Hey everyone. So this is the I think sixth video of the AVL tree series, and in this video we are going to take a look at how to implement an AVL tree. Namely, we're going to implement the insertion algorithm. Now, the AVL tree insertion algorithm, so we're going to start off by taking a look at what we need to change about our regular BST to turn it into an AVL tree. So right here, I have the same code as a regular binary search tree. The only difference is that I took out the iterative insertion algorithm. And the reason for that is because after you do the insertions, you have to fix a whole bunch of nodes starting at the bottom, right? So if we do the iterative insertion, we actually would have to store all of the nodes that we compared against into a stack and then kind of pop the stack to kind of go backwards in our tree. Like that would be the way to do it. So we're going to actually not do that because the code will get sort of like a little bit complicated, and we would actually have to use a different data structure to store the nodes. So instead, we're simply going to do a the recursive insertion algorithm instead. Okay, so basically the same code as the regular binary search tree code, and but uh, no iterative insertion, just the recursive version. Now you will be able to find this code in the course repository when we're done, so you can check it out there, okay, for yourself. Now, so this code is just BST code. The only thing I changed was I renamed it AVL, took out the iterative insertion, and that's it. So what we're going to do now is we're going to take this AVL, this BST code, and we're going to turn it into an AVL tree. Now, an AVL tree is actually an augmented data structure. And what that means is that in order for us to do all of those things that we did in our drawings, we actually have to store a little bit of extra information into our nodes to do this. Because in order for us to determine whether or not we need to do a rotation, we need to know the balance of the tree. So either we store the balance and track that, or we store the heights and we use it to calculate the balance and we have to track the height. We cannot calculate the height at, as we're doing it. And the reason is because to determine the height of a tree, so if you don't know anything about the tree and you want to know how tall it is, you actually have to do a full tree traversal because you have to figure out who's the taller tree. And you don't know which branch will ever be taller. So you have to actually go down the tree all the way through, visiting every single node, which means that the height algorithm, the function for finding the height, is an ON function. It's a full tree traversal. So we don't want to do that. So the only way to not have to actually calculate the height of any subtree is to store it. So, and the height has to be calculated for every single subtree. It can't be calculated as like the height of the whole tree because that's not what we're interested in. We're interested in how tall each of the subtrees are, right? So that's the value that we're going to store. Now, in some books, they say you can store the balance. But in my experience, I have found that storing the balance, it's really hard to figure out what the balance should be after an insertion because it depends on whether you came from the right or you came from the left and whether or not a node was added and whether or not some other, it's just a mess. So personal preference, I think it is actually better to store the height. Okay. So over here in the node struct, I'm going to add an extra data member here called height. When we create the node, we are going to initialize the height to being 1. And that's because when we create a node, it's a leaf node. And if we look at that node on its own, as if as if it is the root of a subtree, it is a subtree with height of 1. So that's where that 1 comes from. It's the height of the subtree with just one node in it. So this is what we have, okay? Now, just to be sure that you can see what is happening, oh, that is not, give me a sec. This is because I turned it off for a sec. Okay, so just to be sure you understand what is happening here, what I'm saying is that in every node, here's a tree, and what we're going to do in this tree, other than store numbers, so this tree has numbers in it. okay? 10, 20, 5, 1, 7, okay? There's numbers in it. But what we're actually storing in addition to the numbers is we're going to store how tall the tree is. So the tree at the root here is, sorry, it's not 0. The tree at the root is height 3, okay? Because this tree is 3 nodes tall in total. At the 5, its height is 2. At the 1, its height is, sorry, its balance is 0. Its height is 1, so, and its height is 7 here. 7 is 1 also, and the height at 20 is also 1. So what we're doing is we're storing the nodes, the height of the trees into the nodes. Now, so storing the height means that we can't use that height value directly. We use it to calculate the balance. So if I want to know the balance of this node here, what I do is I look at the right subtree's height value, and I look at the left subtree's height value, and then I just subtract. Okay, so it's easy enough to find the balance if you know what the height is. So that is what this does. Now, to help us with this, I'm going to actually write a few functions into the node. We're going to add a few functions to the node struct itself. We're going to add a function here called balance. And the balance function, effectively, what it's going to do is it's going to return the balance of this node. Okay, now the balance, remember, is calculated by the height of the right minus the height of the left. Okay, so I'm going to write a variable here called height right, or sorry, height right. Now this value is the height of the right subtree. Now, why is it not just uh, right right underscore arrow height? It's because it's possible that right underscore is a null pointer, and we don't want to accidentally crash our program. So what we have to do first, before we can access it, is we actually have to check, is there a tree on the right? Now, if there is, then obviously this is height arrow, this is right arrow height, right subtree's height, tell me what you are. Now, if it is a null pointer, though, then the height of the right subtree is 0. So we just want to make sure that we don't get the wrong number here. Height left, by the same token, we're going to calculate it as left, question mark. And then if it's a null pointer, it's 0. Otherwise, if it's not a null pointer, then we access the height of the left subtree. Okay, so that's all we're doing with this. Now the balance is simply the height of the right minus the height of the left. So the balance is easy to calculate once we know how tall the trees are. Now we're also going to write another function here that will allow us to update our height. So this function is called update height. And this is called if we think that the height is no longer correct because we added a node into the tree. We want to update the height. Now, updating the height involves basically taking a look at the right subtree's height, the left subtree's height, seeing who's taller, and then using that to update the current node's height. Okay, and the function starts off basically the same as the balance function. We want to know how tall the right tree is, how tall the left tree is, and then depending on who is taller, we're going to update the height with that value. So if the right subtree is taller than the left subtree, then the height of the current node is equal to, height is equal to whichever one is taller. Actually, sorry, let's put the 1 in first. So it's 1 for the current node plus the taller of the two subtrees' height. So whichever one is bigger, if right is bigger, then it's height question mark, height right. Otherwise, it is height left. And I wanted to move the 1 plus to the front instead of adding 1 after, because I actually have to bracket the entire expression. or else it's going to evaluate it as height left plus 1. So I have to be kind of careful about how to do that. And this is the better way to do it. So that's all that is. So in any case, one function returns the balance, the other one updates the height of the node and makes sure that it's correct. Okay, update the height of the node. Okay, so these are just two fairly simple functions that will kind of fix things for us, okay, when we need it to. Now, we have a couple of other functions to write. I haven't actually written them yet. So let's do that. So this is still regular binary search tree insertion. Now, at some point, we have to write a rotate function because we have to rotate our trees, right? So I'm going to write out the prototype and we'll worry about how to code them in a bit, but I want to sort of write it out and say what they do. So we first of all have a left rotate function. And what you pass into the rotate function is a reference to a node, okay? So so I'm going to call it A because it's the pointer to A that we're going to pass in. Okay, the pointer to the node that is plus 2. Okay, so we're going to call it A because that's what it is in all our diagrams. And we also have a right rotate function. So right rotate. And this one is also going to be passed in a reference to a pointer that we always call A in our diagram, so we might as well name it that here. So we have a left rotate and a right rotate. So remember that this is your left rotate, this is your right rotate, okay? So what we want to do is we want to write those functions eventually. We don't have to write them right away, but know that they exist. We will simply make the function call to them, and then I'll code one of them and leave the other as an exercise. Now, over here, what we have is we have a regular binary search tree insertion function. What we want to do is we want to add the AVL part of it that isn't here. So this is not AVL tree insertion yet. This is just regular old binary search tree recursive insertion algorithm. What we want to do now is we want to change this so that after we've done the insertion, after we've created the new node, we want to work our way back up to the parent one at a time. Now, what is actually happening when we make our recursive call is we're actually doing the following to our tree. So imagine that this is our tree right here, okay? We start off with a root pointer, and our root pointer over here points to the root of this tree. So now let's imagine what happens when we make the first recursive call. So when we make the first recursive call, so we call the insert recursive function right here. And what it does is it calls insert with root underscore and data. So what that means is that root underscore is being passed in as the first element and then the data as the second. So let's imagine that I'm putting in the number 30. Okay, so data is 30. We actually don't care about it for our purposes, but let's say that data is 30. Okay. Now, the more interesting part is what happens with root underscore. So I'm passing a root underscore to the function. The function, the insert recursive function, renames it subtree root. Now, this is really important. The fact that this is a reference means that what I'm doing is I'm actually simply calling root underscore subtree root. I'm going to short form that to str, which is kind of terrible, but subtree root, right? Subtree root is actually another name for root underscore. Okay, so my subtree root is actually root underscore when I first make the function call. Now the data here is, so I take the data 30, and well, actually before I do that, I have to check whether or not this is a null pointer. So have we reached the base case? Now in this case, root underscore is not null. So what does that mean? Well, it means we are going to not do this. We're going to end up in this one. 30 is the data. Data is not less than subtree roots data. Subtree roots data is 10. So what we're going to do is we're going to make this function call right here. So subtree root arrow right is being passed in at this point. So what it means is that I'm actually passing in, I'm actually renaming this pointer right here subtree root. So to distinguish it, I'm going to call it the second one. But effectively, it's the subtree root in the second call. So so the right pointer of 10, that is the second subtree root that I'm passing in. Okay, and I say okay. So I go in and I say okay, is this pointer null? Well, no, because I'm pointing at 20, so it's not null. And now I have to compare 30 against 20. 30 is not smaller than 20, so I'm going to do this. And that means that I'm going to actually be passing in this pointer right here. So subtree root 3 is this pointer that's sitting inside the 20, but it is a null pointer. Okay, we're simply renaming it subtree root. So what we're going to do now is we go in and we say, okay, subtree root, that's a null pointer. So we're going to make a new node and make subtree root point to it. So we make the new node 30. Now our constructor, of course, actually sets the height to 1. So I'm going to do that in my code in here. And then, according to my constructor, it says, okay, make subtree root point to it. Now, subtree root in this case is this pointer right here. Subtree root equals to new node actually does that. Oops, sorry, this is the picture. Subtree root equals to new node will do that in my diagram. So that's pretty good, okay? Because it actually points it to 30 without me having to do anything. Now the function finishes. And when the function finishes, what it will do is it will pop the stack. Now remember that this is on the runtime stack. So what that means is we go back to the previous call. So this subtree root, basically it's off the stack now. So the subtree root that we're talking about now is the one that is sitting in 10, but pointing at the 20. Okay, so this is really important. Sits in 10, but points at 20. Okay, so when I talk about subtree root, it means 20 because it's a pointer to that node. But the pointer is the right pointer of 10. Okay, that's where the address of that variable is. But the value is 20's address. Now, what we want to do, so what that means, so how do we fix 20's height? Well, all we have to do is tell 20 to update its height, right? So now we have to do more than this. We have to actually check the balances, right? So after we've done the insertion, okay, so it's really important that we do it after. This is the part we fix our tree here. So this is where we're going to write all the code for the tree fixing. Now, how we do that depends on the height of our trees. So if the nodes balance, so the first thing we should do is we should take a look at the balance. If subtree root arrow balance is equivalent to 2, we're going to do one thing, okay? Now, else, if the balance is subtree root arrow balance is equivalent to -2, we are going to do another thing. That's the 2 different rotations, right? And finally, if it is balanced, what we're going to do is we are going to simply say, okay, it's balanced. So now we just have to make sure the height is correct, right? So we're going to update the height of the tree. Update height, and that is all we have to do. Make sure that the height is correct. Okay. Now that will work for 30 because we just have to update all the heights. Now, if we have to do a rotation though, we have to actually do it in here. So if the balance of subtree root is positive 2, what it means is that we are basically looking at this diagram, plus 2. And now we have to see if b is plus 1 or if b is minus 1. That's what we need to do. We need to check this node to see if it's the same sign or different sign, right? So how do we do it? Well, we call the balance function on subtree roots right. Okay, so if subtree root arrow right arrow balance is equivalent to 1, okay, or well, greater than or equal to 1. Equivalent to 1, I think is fine. If it's equal to 1, that means that we do a single rotation. Okay, we haven't actually coded it yet. Otherwise, okay, if it's not 1, it's minus 1. We do a double rotation. Okay. Actually, yeah, I don't like that. If it's equal to minus 1, do a double rotation. Otherwise, we do a single rotation. Okay. I'm trying to remember, if you do a deletion, I think there's a chance that it might be 0, and I think for 0, you just do single. But in any case, it doesn't matter. This is good enough for our purposes. If the signs are different, do a double rotation. Otherwise, do a single rotation. Now, over here, for the other version, it's actually exactly the same, just in sort of opposite direction. So instead of minus 1, it is when it's plus 1, you do a double rotation as opposed to a single rotation. Now, how do you actually do a rotation? Well, let's put them in, right? So remember that this is our situation. So if we are too tall on the right-hand side, the double rotation, we first have to do a left rotation here at where C and B are. So we want to rotate to the right at one level below, followed by another rotation up top. So what that means is that our double rotation is going to be 2 single rotation calls at different levels. Okay, so remember that when we were looking at this, the double rotation is actually just 2 single rotations at different levels. That's how we're going to actually do the implementation. Otherwise, we have to write a double rotation function, and we could do it. It's just, lazy. It's faster to just do this. So double rotation goes like this. So we're going to start one level lower. We're going to rotate to the right. And then we're going to go one level higher and rotate to the left. Okay. So that's sort of the code. So right rotate followed by a left rotate. So what we're going to do is we're going to start off by doing a right rotate at subtree arrow right. So take the right subtree and do a right rotate on it. And then we are going to left rotate subtree. Oh, subtree root, sorry, for both of them. So a double rotation is simply 2 rotations in opposite directions at different levels. Deal with the child first, do that rotation first, and then do the other one, okay? Now, the double rotation over here for the minus ones is basically just an opposite direction. So this would be a left rotate first on the subtree root arrow left, followed by a right rotate subtree root arrow right, or subtree root, sorry, that's it. Now, if it's a single rotation, then it's just a left rotate here, and it is just a right rotate for this one. Okay, So single rotation is just one rotation. We don't have to deal with both. Okay. Now, once we finish the rotation, okay, we have to update, we have to ensure that the heights are correct in all the subtrees. Now, if we do a double rotation, then remember that there are 3 nodes where the heights might change. So A, B, C, those are the nodes we have to care about. So I'm just going to update the heights of all of them, okay? So, which is pretty simple to do because we have a function to do it, right? So subtree root arrow left, arrow update height, followed by subtree root arrow right, arrow update height. Those are function calls, so make sure I do that. And then we also have to make sure that the current node's height has also been updated. Arrow update height. Okay, now there's probably some ways that you can do this that's a little bit more efficient than this, but this will be fine for what we're doing. If we do a single rotation when we're done, it will be left and the root. Why is it left and not right? Because right was the taller one, right? The reason is because after the rotation is done, okay, this is the situation we're in, A is on the left. So that's the one that's going to be wrong. So A and the current node, okay? So left and the current node. And the rest of it is actually the same for the double rotation. And for the single rotation, um, we are going to not update the left, we're going to update just the right, and that's all we will have to do. So this is how we basically write the AVL tree function. The only thing we have left to do is to code each of the rotates, okay? So this is sort of like a programming process, right? Like, and what you want to do is you want to take your algorithm and you sort of work out the big steps actually first. So I actually didn't really look too hard at how to do a rotation. Like I still don't have the code for it, but I do have sort of stub functions ready to go. The moment that I finish writing left and right rotate, this should work. Now, there's probably a bug somewhere that I typoed or something. We'll figure that out. But in any case, we only have to write left and right rotate. So let's do it, okay? Here's the diagram of what we want to do. Now, when we were talking about it, remember that I said that, well, you know what, left and right rotate, all we're doing is we're just reassigning a bunch of pointers. That's all that is. So right here in this diagram, actually, let me see if the diagram is still around. Let's go back to it. No, I erased it. Okay, oops. All right, so let's redraw the diagram over here very quickly, just to sort of see where we would be with it. So basically, our function for left rotate, what we want to do is we want X, Y, Z, A, and B. Those are the nodes, right? Now, what we are going to be getting, though, this is the way that it looks. This is what we want: A, B, X, Y, Z. Okay, when we're finished, this is, oh, sorry, this is wrong. This should be B up here and A. So now that's the diagram. Now in code, it's a little bit different. Okay, in code, A, and A is actually a pointer to the A node. Okay, so this is variable A in my picture. And what we want to do with variable A is we want it to point to the B node. Now, we can't just do this without actually, we have to be very careful not to lose part of our tree. So this is what we're going to do. I am going to declare a bunch of variables, okay? So the first variable I'm going to declare is a pointer called B, which points to B. So B is A's right. So A arrow right is B. So I'm just going to create a variable called B that will point to the B node. I also don't want to lose Y because that's the other one that is potentially problematic. So Y is equal to B arrow left. Okay. So what this will do is it will actually create two variables, one called B, which points to B, and one called Y, which will point to Y. So that's what I've done. I've created these three variables essentially. And this will allow me not to lose any part of my tree. Okay. So that's now, is there faster ways? Maybe, but this will be fine. So over here, what we're going to do first is we're going to make B arrow left equal to A. Okay. A arrow right is going to be equal to Y. And finally, A is going to be equal to B. And that is effectively what we're doing. And by having the local variables, we won't lose any of our trees ahead of time. Okay. So that's all I'm doing. I'm actually literally taking this picture and implementing it here. Okay, now the right rotate function, how does this work? So the right rotate function, we know we basically do the same thing, okay? So this is right rotate, okay? The pointer starts off pointing at A. So we're going to say, okay, where's B? B is actually A's left in this case, right? Whereas Y is equal to B's right. So we're going to start by creating these pointers. Then we simply reassign them, okay? B arrow right is now going to be equal to A. A arrow left is going to be equal to Y. And finally, A is equal to B. And so that's all I'm doing. I'm changing really these three pointers. Okay. The first two lines is just to make sure I don't lose anything and I have easy access to those particular nodes. That's it. That's the rotate function. 5 lines of code. We're done. Now, obviously, we should test our program because, as I said, there's a good chance that I have a bug somewhere. Let's take a look. So this is the same as my BST main. We can test this out if you want, but we can also test some other data as well. So let's see. Let's actually instead of testing this, let's test the example we had done earlier in the other video. So in the other video, we had inserted a whole bunch of values, and if I keep scrolling up, I'll have it. Let's insert 10, 20, 30, 40, 50, and then 25, okay? So 10, 20, 30, okay? 40, 50, and finally 25. And let's see if we are able to get the right values back for us. And we'll also print them out and see what we get. Okay, so here we go. So clear. All right, C++ AVL main.cpp minus std equals C++ 0x. And, ooh, no, doesn't like something. All right, so first of the typos. Let's see. Oh, okay, this is a function call. I forgot my brackets. So let's see, what line is this? 67? So 67, this should have been balance, like that, not. So that bug is it elsewhere? Oh, I only did it in that one place. Okay, good. Still more. So I have one error and several warnings. Let's see. Ooh, right here is, so this is asking, has lower precedence than brackets. That's fine. Okay, I see what it's saying. Okay, so maybe it doesn't like the way that I'm doing the conditional. So, stick a whole bracket around this whole thing and we will be good. Okay. Now, the error, that's just a warning. The error of this is over here. Oh, we still have I guess we do have the same bug. I just didn't catch it. Okay, there we go. So it's a function call, it needs brackets. Insert, okay, that's just telling me where things are. So, okay, let's give it another go and see what other warnings we have. So, hey, that's not bad. Fixed. All right, let's go. Let's run it. Does it work? Well, if it works and we're going across, what we should see is 30, 20, 40, 10, 25, 50. Do we have that? 30, 20, 40, 10, 25, 50, right? In order is correct, 10, 20, 25, 30, 40, 50. So this probably is the correct tree. So yay. All right. So in any case, that's pretty much it. Thanks.